Hello, my name is Barry Gaspard and I'm going to present to you the proof of concept, a working proof of concept of the vulnerability published by Microsoft called CVE-2020-0601 called Windows CryptoAPI spoofing vulnerability. Here is my Windows operating system that is vulnerable to this attack, and I'm going to demonstrate how this vulnerability works, because this vulnerability actually is based on the way Windows CryptoAPI found is a function found in the Crypt32.dll library. The way it validates the elliptic curve cryptography certificates, it makes it very vulnerable, because an attacker can gain advantage of this and then create a spoofed CA that will be trusted by the operating system. So a basic understanding here is, for example, if I want to, I am requesting for a website, for example, let's say Windows is a client on Windows using a browser, let's say Internet Explorer is requesting for google.com. When Google sends its certificates signed, for example, by a certificate authority, let's say, for example, let's encrypt, the Windows operating system will verify if this certificate is indeed signed, if this certificate sent by Google, for example, is signed by Let's Encrypt, and if it's validated, it keep it in the cache. So this is where the attacker will gain advantage, because when it keeps it in the cache, any subsequent request, he will, to speed up the connection, Windows will instead verify the public key and the serial number of the incoming certificate. Once it's valid, it will then use the trusted CAs in its trust anchors located in the cert manager of Windows, and then it serves this website using the TLS secure connection. So that is the way attackers can use. So because of that, since Windows CryptAPI is not verifying the elliptic curve parameter, which is PA, like generators and the rest, attackers can forge a certificate. Why? Because in elliptic curve, the basic is like the low-level concept is that we have a public key which is equal to x times the generator. Let me increase that. Okay, all mod P, of course, mod a certain P, mod P. So we cannot say that we will okay, whatever. So we consider this mod P. This is the public key, this is the private key, and this is the generator. This function, this equation work in mod P. So this, if we imagine, for example, if we take the Microsoft root CA, product root CA, ECC, which is having a public key and which is found in its certificate that we can extract with just by going to the certificate manager of Windows, and then we export it in the form of DAR or any format we want. That is the only thing, plus the serial number that CryptAPI used to verify whether the certificate is trusted or not. So an attacker can force these parameters, this private key and the generator, to have the same public key as that of Windows. The scenario here, the easiest way to do it is to set the private key X, which is an integer, to 1, and this generator automatically, the simple basic mathematics, G will become P, because if X is 1, G times 1 equals G, which is equal to P. So G here that we created will become equivalent to the public key of this Windows root certificate. If we are taking, for example, the case of Windows root certificate, this is the basics understanding of how this vulnerability works. It's a simple mathematical error that Microsoft actually did, because they just verify the public key and the serial number. So based on that, attackers could do a lot of things, like for example sign even exe files on the operating system, and then the Windows, because Windows will trust the certificate, because it will appear as if it was a Windows certificate, so Windows will trust it, and then it will appear as a legitimate exe file. I will demonstrate a proof of concept on this machine, where we will use Windows certificate that I already extracted, and there is a Python proof of concept by OLEDB that I will share the links of all the details here. Okay, so before it's not a Python, sorry, a Ruby proof of concept for this case. Let me see. Cut. Great. So this code is simply a very simple code. argv here accept value from the command line, meaning if we run ruby main.rb, we need to put an argument, and that argument is the certificate that we are going to put, the certificate in a dir form, in a base 64 form. So once we put it, it will, this line here will read that certificate and create a spoofed CA. It will take it as an input called raw, because we saved that in the raw variable. So from there, it will generate and parse the public key from the CA that we input using the dir format. It will parse the public key. It will set our private key. Remember here, oh, I closed that. Remember that we set x was 1 and g. So if we set x to be 1, the public key will be equal to the generator. So that is the idea here. We are setting the private key to be 1 so that the public key will become the generator. The public key and the generator will be the same. So the CA key will be in, we will take the group in the group method. So we will set the generator to the public key that we extracted, and the parameters, the curve parameters that this CryptoAPI is not verifying. So we set this to a normal explicit curve ECC format that we are going to use, and then we are going to insert it into the file system in the form of .pem. So this will make the file system have the certificate. Okay, so let's now go. I think I have the steps here. Let's see that. I don't know if the steps. Steps. Great steps. Yeah. So okay. The first command here. Sorry. The first command here, as I said, we are going to use this Ruby code in order to input the certificate that we copied from, we extracted from Microsoft Office. We can also use OpenSSL S-Client Connect, and then the domain name and 44. We connect to the port 443 for SSL certificate, and we extract it also from there using OpenSSL S-Client tool. It depends on all, and then we export it in a format that is suitable for the Python code, so that we can manipulate the certificate and extract the public key and generate it in a form that we are going to use it for our spoof CA. So it depends on how the use case or the person needs to manipulate this system, but it is dependent on how the person wants to do it. Okay, so here we are using this Microsoft Certificate Authority, root certificate authority. Okay. Okay, we extracted okay, let me show you. We created the spoof CA key that we remember. From the key we produced the PEM file that we inserted into the file system. So we will generate a new X509 certificate based on this key. So we will just use the default config because we are not going to, Windows will not even verify this. Okay, great. Great. Spoof CA, CRT, great. Okay. So we are going to generate a new key that we are going to use to create the SSL certificate. Perfect. So the next step here, we are going to create a new certificate signing request. Remember here, we can also use, we can modify the spoof ca.conf and put the domain that we want. But for this purpose, let me just show you TLS. You see the domain here, google.com, the CNAME. Yeah, we are going to, if for the future, you can manipulate it and change and do whatever you want to do. But for this proof of concept, I'm going to use google.com for that. So you can change it in case you're interested to test with other domains. Sorry. Oh, great. Okay. Next, we are going to sign our new certificate signing request with our spoof CA and the CA key. Yeah, they have properties of expiration and the rest, but what we are going to do is so that we can use it in our web browser. Great, we signed it. Okay, now we can normally copy this. Let me show you what has been added. We have this cert.crt, cert.csr, like certificate signing request, cert.key, and then spoofca.key, spoofca.srl. Okay, we are going to use cdtls, a proof of concept a proof of concept node.js server that we are going to use for the man in the middle, because we are going to perform a man in the middle attack where the user will browse our web server and then it will appear trust, as if it was the original or the trustworthy web server that the user knows. So for that reason, I prepared a remote desktop Windows, as you saw in the beginning, that is vulnerable to this. And this Windows machine is I also added a host file here. This our proof of concept involves Google. I will also make some proof of concept with other, like nsa.gov. Yes. So this is the DNS file. For example, this part here. This part here, resolution is handled within DNS itself, but it's the host file. We all know how the host file functions. It maps the IP to the domain name. So it's already saved and all set before the stuff. Remember here now is not functioning because it's offline. I have not yet launched the server, the node.js server. So let me launch the node.js server, index.js. Excuse me. Oh, we need to install node.js, work with npm, node packet manager. We need to install Express for this. npm install Express. Great. So we launch our node. Okay, our server is running. If we know run netstart.plan2, we can see it running actually, but I already know it's running. Let me close this. Okay, just for those who may not know, this is the way to extract the certificate. This is the cert manager, cert mng.msc. This is the trust root certificate authorities. This is where Microsoft takes its trusted certificates and validates using the CryptAPI. So the Microsoft ECC certificate, Microsoft root, yes, Microsoft root certificate authority. Great, this one. This is what we are using, Microsoft ECC product root certificate authority. Okay, so we run our node.js is running. Okay, so let's you can export it if you want. Open. This is the detail here. You see Microsoft is using elliptic curve, and then there is the public key here that we extracted using the Ruby stuff. We have also the serial number here. So everything is there. We can say copy it to a file and then next, and then we select the format we want, and then if we save it, it will be in the form we want, and then we can see in this form. Okay, you can also use OpenSSL if you want, it depends. Okay, so let's try google.com. What is going on? Okay. Oh, sorry, let me modify this to point. I forgot to even introduce you. This is Node Packet Manager. Node.js is the JavaScript backend server, and it is working with JavaScript, of course, and it's using npm as we said. Let's say you have been curved. You have been curved by. Okay. These are the key, the certificates, and all the spoof CVEs. We are using it for the validation and verification using the CryptAPI. And remember, Google is using implicit TLS, so we need to use port 443 for that. Okay, so we run our node.js again. This time around, let me close this and open again. Voila! Great. You have been curved by. If we check the certificate, it's valid. Everything is valid. You see, certificate is valid, issued by Oli found, sorry, and then the subject and so on and so forth, serial number and everything. You get it? So we see that it's working with that. With this technique is working, so we can successfully man in the middle for this. Okay, so excuse me, let's go to the next. Another person called Salim Rashid, yes, he also demonstrated another proof of concept, and then I'm going to demonstrate it here. So he used basically the same ideology, but here there is a Python code that I'm going to explain that is happening. What is happening? Okay, it's pretty much long, but I'll briefly go through it. He imported the necessary library used for the process. He is using OpenSSL. He is using OpenSSL for the creation of the keys and the certificate at the same time. and then tuning the parameters of the curve. You see here, he tunes the parameter of the curve to make sure that it resembles the public key, because you see, remember, x is equal to p is equal to xg, and then he wants to make it in such a way that the parameters will be tuned with the private key in order to be equal to the public key of the host trusted root CA. So these are the parameters, of course. So he's using X500 to produce a certificate, and then he will, of course, tune it also. He will generate a private key. These are all functions that he is using the def function, and then he will generate serial number. You remember the verification process is against the private public key and the serial number, so he's generating the serial number based on the previous certificate, and then he will write it to the system, and then he will use a write PEM. You remember, write. This is write binary using file manipulation, authenticate certificate. So this is basically it. What we are going to test here, we are going to test for, and then he will create the certificate using the certificate of authority and so on and so forth. We are going to test for nsa.gov, and we will use the PayPal certificate, because above we use PayPal certificate for. We are going to use the PayPal certificate. The PayPal certificate, let me just show you. PayPal Komodo Certificate Authority can validate PayPal, for example. Excuse me. So based on that, we will run this Python okay, so we create using curve parameter of p prime 26. Based on defined per curve parameters prime, this will have specific G, specific sec P will have specific G, specific parameters for creating the private key in elliptic curve. So we will write the certificate, the intermediate CA, and then we will write this the key, the private key that we are going to use, and then we will generate the authentic code, and then writing the RSA key, the local. We will use this local key for as an input in order to spoof the web server so that it can recognize our spoof CA. So for this proof of concept, we will use the folder www ls okay. Okay, this was no index. Okay, proof of concept testing by. Okay, let me just change. This is for OT lab, meaning offensive technology. Okay, so slash http. Sorry. We are running a Python. Let me run a Python simple HTTP server here, which also takes this IP, the local host, and then the 443 implicit TLS as it's a simple script to run a simple web server using Python, actually, and it accepts the certificates that we just recently created as arguments here, like certified. Okay, so HTTP local key to local.key. Okay, our server is running, and remember we change the host file because we want to just simulate. It's a proof of concept we want to demonstrate. So you can see nsa.gov nsa.gov and pointing to this. Okay, nsa.gov. Perfect. You see what we just changed? OTLab. Yes. So you see, Komodo CA ECC nsa.gov. This is a proof of concept to demonstrate that we can man in the middle. This scenarios, many scenarios exist. I don't want to make this long, otherwise we can also use this CA to sign an exe file, that a binary that is not recognized or non-publisher, to sign it by our spoof CA, and then Windows will recognize it. There are many techniques, many other vulnerabilities that can be arising due to, not vulnerabilities, but threats that can arise due to this simple mathematical error or mathematical problem. Okay, so thank you, and thank you very much.